All right, hello and welcome. Thank you for joining us today for this week's session of the Parks College Weekly Webinar Series. My name is Amy Price and I am the Outreach Coordinator here at Parks College. I'm joined today virtually by Dr. Scott Sell, who will be introducing us to some biomedical engineering graduate students and showing us around the Tissue Engineering Lab. We're so excited to have you joining us today from wherever you might be. Thank you for taking the time to virtually visit us and learn more about the engineering programs at St. Louis University. In total, Parks College has programs available in aerospace, biomedical, civil, computer, electrical, and mechanical engineering, as well as flight science and aviation management and engineering physics. We hope that you will see or hear something today that piques your interest. Before we start, I did want to give you an idea of how the webinar will flow. I will soon introduce Dr. Sell, who'll be showing you around the lab space and sharing information about the biomedical engineering program. He will then introduce Park students Elena, Gabby, Abigail, and Eileen, who will share their research and their experiences of being engineering students with you. And finally, we'll conclude with some time for questions and answers. So throughout the webinar, please submit any questions you may have to the Q&A feature at the bottom of your screen if you're viewing this through Zoom, or in the comment section if you are viewing through Facebook Live. And we'll do our best to answer as many questions as possible in the final 5 to 10 minutes of our session. Throughout this webinar, you don't need to worry about turning off your microphone or camera. You can hear and see our presenters throughout the webinar, but we can't hear or see you. Finally, if you have any technical difficulties during the webinar, please email parksevents@slu.edu and we will help address any issues that arise. This session will be recorded and posted to our YouTube page in the next day or two, and you'll receive an email with that link when it becomes available. So now with all of that housekeeping out of the way, I am very happy to introduce Dr. Sell and the Tissue Engineering Lab. So Dr. Sell, I will turn it over to you now.
Hello, I'm Dr. Sell. I'm the Biomedical Engineering Program Coordinator and I also run the Tissue Engineering Scaffold Fabrication Lab here at St. Louis University. Generally speaking, our lab works on tissue engineering, so the creation of off-the-shelf tissue alternatives for things like skin or bone or cartilage. And my lab specifically focuses on the scaffolding, the extracellular matrix. So we try to recreate extracellular matrix analogs using a number of different polymers and fabrication techniques. So if you think about a tissue, the two main parts of a tissue are going to be the cells and the extracellular matrix. So if you were to remove the cells from any tissue in the body, you're still going to have an extracellular matrix or a scaffold that can drive and control the regeneration and repair and construction of that tissue. So my lab works to utilize things like collagen or elastin, synthetic polymers like polydioxanone or polycaprolactone, and processing techniques like electro spinning, hydrogels, and cryogels to recreate those extracellular matrix analogs. We're going to show you around the lab and highlight 4 different fabrication techniques. So we're going to start with electro spinning and my PhD student, Elena.
Hi, I'm going to introduce you a little bit about electro spinning. So the cool thing about electro spinning is you're actually charging a solution to make nanofibers. So you can do synthetic polymers or natural polymers. So what we have is in a syringe pump, we actually can load in our solution and we regulate the flow. And then we attach a needle. And to that needle, we attach an alligator clip so we can add a voltage. And that voltage charges the solution particles. And so now that all these solution particles are similarly charged, they're actually going to be forced out and they're going to form this Taylor cone. You can't really see the Taylor cone, it's super tiny. But from this Taylor cone, jets of solution are actually going to be expelled, and then the solvent rapidly evaporates off of it, and you get these nanofibers, which is kind of like almost like pieces of spider web that come off, and then they're attracted to this mandrel, which you see rotating around, because behind it is a grounded source. So we created a potential difference, so we're attracting these fibers over. So as it's rotating, it's collecting all these fibers and it keeps overlapping. So then you end up, if you electrospin for a really long time, you end up with a sheet that you can cut off this mandrel, and it's like an actual 3D mesh. So it's kind of like spider webs all layered on top of each other. And then we're able to use this in different tissue applications.
So that's electro spinning. It's a relatively old technique, but it's been revolutionized with tissue engineering. And so it's a great way of producing nanofibers, so things that are significantly smaller than a human hair in diameter. And we use it for things like burn dressings or skin grafts. We use it in things like bone applications. And so it works as a really good extracellular matrix model or scaffold. The next thing we're going to look at is going to be a modification of the electrospinning process. And another graduate student, Gabby, is going to share with you kind of a combination of additive manufacturing and electrospinning.
So I focus more on near-field electrospinning, which is taking the electrospinning technique and putting it all in a much smaller scale. So you have a smaller flow rate of the syringe, you have a smaller voltage that you use, and a much smaller working distance, so the distance between the needle and your collecting plate. Essentially what this does is you'll still be getting the unaligned fiber meshes, but I'm trying to combine it with 3D printing so that I can control the pattern that I am creating with my prints. So it's set up quite the same, but I have tubing connected down into the fiber or into the printer head so that I can have control and I can program exactly what I'm printing. An example of that is here is an unaligned print, and then there is a print with straight lines.
And so looking at that, utilizing additive manufacturing combined with electrospinning technology, we can really precisely deposit where those nanofibers go. So we can utilize that for some specific patterning. So if there's specific scaffolds in the body that tissues have unique patterning, so things like blood vessel has unique patterning of the extracellular matrix, or the cornea or the eardrum, we can replicate those patternings utilizing that near-field electrospinning to control and deposit electrospun nanofibers. The next thing we're going to look at is going to be alginate, and I'll introduce Abby, who's going to be another one of my graduate students using an alginate hydrogel.
Hi, so I work with Alginate, which is a natural material that comes from algae. It is an anionic polysaccharide. Due to its properties, it's very favorable in biomedical engineering. It has the ability to interact with different cations like calcium and barium. It can undergo ionic dilation as a result of the interactions. Alginate is biocompatible, non-toxic, and biodegradable, and that's why it is favorable in DME. Alginate has many applications, both in the commercial and private sector. It can be used as thickening agent, for example, in ice cream, cosmetics, toothpaste. In industry, you can actually use alginate for dentistry, prosthetics, and wound healing. For instance, in wound healing, you can use a super absorbent dressing. Alginate can also be used as a drug delivery vehicle, where alginate can be fabricated into different shapes and sizes. So here I have some examples of what we can do with alginate. So as you can see here, we have some calcium carbonate hydrogels, and we can manipulate the shape and size and thickness as well. And I also wanted to guys showcase to you different, what I said before is manipulating alginate to different shapes so you can make different thickness. This is actually copper carbonate. And another cool neat thing about alginate is you can also create beads. So I'm going to do a quick demo. Here we have calcium chloride, and alginate is in the green, and you can see as I load this in there, you'll start to see beads form instantaneously, and that is due to the cross-linking. So, and you can again manipulate the size or the viscosity of the solution. Yep, and that's pretty much it. That's what I work with. Thank you for listening.
So those were alginate hydrogels, something very, very different in terms of the chemistry and the control and then the manipulation of those polymers. The alginate hydrogels, you can see they look very different structurally than the electrospun nanofibers, and we can utilize them for a number of different tissues. So where we saw those nanofibers with the electrospinning, we can use those for skin and wound healing. With alginate, we can use those for things like cartilage or even bone. So thinking about the next step from hydrogels is going to be cryogels, and another graduate student, Eileen.
Hi, so I work with cryogels, which are similar to hydrogels in that they use a polymer and they are cross-linked. So those polymer solutions make a 3D structure, but while they are cross-linking in that mechanism, they are under freezing temperatures. So they make crystals, which create really macroporous structures, just like this. And they're like, sorry, my nails. There. They're like really sponge-like and really squishy compared to hydrogels.
so they're a little bit more robust in terms of mechanical structures. And I usually use also like natural materials, just like the hydrogels, but I use gelatin, which is a derivative of collagen, and we can also use other natural materials to use that to help cell infiltration, cell attachment, and cell differentiation in like a 3D structure.
So that was the last scaffold fabrication technique that we utilize is cryogels. And so similar to a hydrogel, and then we start with a polymer solution, but instead of it polymerizing at room temperature, it polymerizes while we freeze it, and it creates this large macroporous structure. So we can utilize that in things like bone. So even though it looks very spongy, it has a similar structure to bone, and so it does a good job of replicating the bone's extracellular matrix. And so we have the ability to utilize things like chemistry to create these different scaffolds, and then in the lab, assess these different scaffolds. So a lot of times we'll do things like mechanical testing and mechanical evaluations. We'll do biological evaluations, looking at the cell interaction, and then ultimately do implantations in animals and look at animal studies before we design products for use in humans. And so that is all we had to show in the lab, so happy to answer any questions.
Yeah, thank you, Dr. Sell, and thank you, Elena, Gabby, Abby, and Eileen. Very cool that we get to see up close what you each are working on in your research. So for any of our viewers, if you have questions for Dr. Sell or for our students, please feel free to submit those to the Q&A feature if you're watching through Zoom, or on the comment feature if you're watching through Facebook Live. But Dr. Sell, I have a question to kick us off. So you're doing research on materials that eventually would be used in a clinical setting, correct?
Yes, absolutely.
So what are the steps that happen between what goes on in your lab space, and maybe what is the time process between your lab space and getting those materials in the field?
Yeah, anytime you go from benchtop to bedside, there's going to be a large regulatory process. So when we think about developing a tissue engineered medical product, it's probably going to be about a 3 to 7 year process in total. So starting off with some of the in vitro research that we do here, the next steps would be demonstrating some of the safety and efficacy, thinking about ultimately going through the FDA regulatory process. They're also going to see some animal testing. And so we don't do animal testing in this facility, but we have collaborators on the medical campus that will do those animal tests. We have moved some of our products into animal testing before. So we've done some work with some of our Electro Spinning materials in diabetic ulcers in mice and rats. We've done some pressure ulcer work in mice and rats. We've used our cryogels in cranial defects in mice and rats for bone regeneration. And we've utilized our hydrogels in rat femoral defects as well. So we've done some animal work. And then once we get good data on the animal work, the next step is a big step, and that's going to go into human trials and human testing. And so identifying ways to do that in humans and collecting data there to move through that FDA regulatory process. And like I said, it's usually about 3 to 7 years from start to finish going through the FDA.
All right, thank you. And could you, so all of the students that we just met, they are graduate students here at SLU and Parks College. Are there undergraduate students who get to use this lab space or work in this lab space?
Yeah, absolutely. I think one of the things that we pride ourselves on at SLU BME is the involvement of undergraduates in our research. And so we all have probably between 5 and 10 undergraduate researchers. Obviously now with pandemic conditions, face masks, but so it limits our ability to have undergraduates in the labs, but normally we do. We have lots of undergraduate researchers, and we pride ourselves on having those researchers not just doing dishwashing or watching graduate students doing research, but actually getting tangible research output. So getting their names on publications or their names on abstracts and presenting that data at national meetings like the Biomedical Engineering Society is something that we definitely push for.
Excellent. Yeah, and for any viewers who have been attending some of our previous webinars, you've heard from undergraduate students who've gotten involved in research. So it is pretty much across the board in all of our programs. Dr. Sell, I'm wondering if you could take us to some of the students, maybe Eileen or Gabby, who are undergrads at SLU, and if they could talk about their decision to go into biomedical engineering and why biomedical engineering at Parks.
Sure, absolutely. I'd be happy to do that.
So I chose it because I originally wanted to go into med school, and I thought it was a good idea for some reason. And then it didn't end up going to med school because I saw how much work it was going to be. So I just kind of took the path of low resistance, and so now I'm doing a PhD here. So yeah, med school just been a lot of people you have to talk to. I really wasn't into that. So I was really more on to the designing end of things and like kind of more creating things instead of like people. So that's kind of why I'm here. And I thought BME was cool just because you could use a lot of those other skills to kind of like create things, and it's more like testing and you feel more accomplished by doing tasks, I guess.
Yeah, I was kind of the same way. I'd always been interested in engineering, more like the building aspect of things, but I also really like the medical side. So BMU was just really the perfect combination of combining like medical technologies with like math and science as well, because you don't really use as much of that in the become like the doctor or physical therapist. But yeah.
And Gabby actually did the 5-year BSMS program. So could you kind of add a little bit about that process?
Yeah, so I combined my master's degree path with my undergraduate. So my senior year, I was working on my thesis as well. Like it was my combination with my senior capstone. So this year I transitioned just to being a grad student. But it's helping, it really just, it was part of being like in undergraduate research. I figured out that I really enjoyed doing some more of the research technical things like that I didn't really want to go right into industry right away. So by doing that, I just kind of naturally followed in the path of grad school.
Awesome, thank you both. Dr. Zoll, maybe this is a question you can answer, but maybe somebody else in the lab has some thoughts. Can you expand a bit more on career opportunities from biomedical engineering? So we heard med school thrown out, we've got some researchers in the lab, but what does a degree set students up for?
Absolutely. So every year, if we're talking about the undergraduate population, about 1/3 of our undergraduate students come in identifying as pre-meds. And so they'll utilize a pre-med track that we have, right? So thinking about this as a pathway into medical school. 1/3 of our students come in thinking about industry. And so getting a 4-year degree and then going into industry. And then 1/3 of our students think about graduate school and doing graduate research. And so every year it's about the same breakdown. And then the places where our students go, so the ultimate careers that they end up in, there are a large amount that go into medical school. And I've found that being an engineer and having that engineering background really does a good job of preparing people to critically think and solve problems. And so they usually make really good physicians. We also send a large amount of people to industry. And so they'll go to industry and they'll work in places that do research and development. So they may do some product development. They may do quality controls and testing. They may go into regulatory. So they may work for things like the FDA and looking at the development and controls of processes there. They may go into patent law, so a number of students will go into patent law and look at careers there. They may do startup companies, so a large number of biomedical engineering students actually are interested in entrepreneurship, and so they may take opportunities here at SLU with the Center for Entrepreneurship, or in the St. Louis metro area, thinking about the Cortex Center and a lot of the biotech and biogenerator things that we have, and actually develop companies or work at startup companies doing research and development there. When they go to industry, it can be large-scale industry, so we have BMEs that go to places like Boeing or Medtronic or Smith & Nephew, Johnson & Johnson, Abbott. We also have people who do kind of stay in that startup route, and so they're working at smaller companies developing new technologies. And so we really have students kind of across the board at a bunch of different places. They also can go and work at hospitals. So if they're interested in doing clinical research, the VA hires a number of biomedical engineering students every year, so they can work hand in hand with physicians, hand in hand working with patients every single day, rounding and basically utilizing biomedical engineering technologies in a hospital setting or doing patient research. And so things like spinal cord injury and rehabilitation, physical therapy, they really have a large need for biomedical engineers. And so you don't have to be a physician to work with patients. You can be a biomedical engineer and find some of those jobs that allow you to have those opportunities as well.
Awesome, thank you. Yeah, I think you really highlighted so many opportunities just in St. Louis for biomedical related careers, and yeah, all the various career paths that come out of that. For students who enter the program, do they need to know right away kind of which track they're setting themselves up for? Or is that something that they can explore while they're, in their freshman and sophomore year?
No, actually, and I'll let you talk to Gabby about that.
Awesome.
Yeah, it's definitely something you can explore. Generally, if you want to go the pre-med track, you pretty much start off pre-med, but there's flexibility in like figuring out if that is something you want to pursue or if that isn't, because a lot of people will figure out they really do like biomedical engineering and want to do that as a career versus being a physician, kind of like what Eileen was saying. But then as you go further up into your second or third, fourth year, you really get to start picking the electives that you're more interested in. So say you're more interested in research, you can go into, we have a class called brain-computer interface. So it's more about like the electrical side of things, or you have like tissue engineering, and you look more at the cellular and molecular level of biomedical engineering. So you really have control, well, somewhat of control over like what path that you go down.
And the curriculum is definitely set up for some flexibility. And so even though students may start in pre-med, they don't necessarily have to stay there. They can switch back and forth and move pretty freely back and forth between those different tracks that we have. And so we see that all the time, because really the framework for all of those different tracks is about the same. It's just basically which elective courses our students take. And so the pre-med track loses a little bit of flexibility because of some of their pre-med requirements, but for the most part, everything else can switch back and forth and shuffle up the electives that they're really interested in.
Thank you. Yeah. Could you explain a bit more, or kind of just embellish all of the different areas of research that exist in biomedical engineering? So here we saw tissue engineering specifically. About a month ago, we visited the surgical robotics lab and saw that, that kind of research in the medical field. But what else is going on?
Yeah, biomedical engineering is extremely diverse. So even though it's one of the newest branches of engineering, you think about things like civil or mechanical engineering as being very traditional engineering. BME is relatively new, but it's diversified very quickly. So you have things that are definitely more electrical centric. So you talked about brain-computer interfaces or the medical robotics, bioelectronics and imaging. That's a big part of the electrical focus. We have things that are more mechanics focused. And so you have fields of biomechanics or orthopedic engineering working specifically with those joints. Rehabilitation engineering, so Dean Sabick does a lot in terms of biomechanics and rehabilitation. And then you also have things like the biomaterials side of things. So looking at tissue engineering, biomaterials development, the implementation of these materials, the animal testing of these materials. So there's a wide range of things that fall under biomedical engineering as an umbrella term. And you're starting to see a lot of kind of cross-pollination between these. So we do a lot of work with our Center for Additive Manufacturing. We do a lot of work with some of the additive manufacturing components. A lot of the imaging things are really important that we utilize in tissue engineering. So there is a lot of overlap between some of these emerging areas in biomed.
Yeah, lots of opportunities for collaboration and yeah, even more unique and different research is coming out. Could we just spend the last couple minutes? Would you mind taking us around to each of our students, and could they share what their personal career goals are or what they're hoping to do?
Absolutely. So we'll start with Elena.
I'm actually kind of a non-traditional student. I finished my undergrad and I went into industry, and I kind of started working, and I was a chemist, but I started kind of getting into more biology stuff. So I actually came back to graduate school because I want to do more with like the chemistry biology interface. So that's kind of where biomedical engineering fits in.
I'm still trying to figure out exactly what I want to do, but I think I'm leaning a little bit more towards clinical research because I do like the idea of having patient interaction or doing something like that, or the industry anywhere in tissue engineering, I think would be where I'm at.
So I still have no idea what I want to do. I just kind of like day by day, take it task by task. But eventually I just want to get like a job that pays the most that I can get because I want to make a lot of money.
Hi. So prior to coming here, I actually worked at a startup company in Chicago, and I really like that. Basically, it's not traditional day-to-day. Everything changes. So coming here, I really get to explore the R&D side. So definitely after finishing up here, I would like to go work for a startup company. maybe start my own. So.
That sounds fantastic. Yes, thank you. And Dr. Sell, before we wrap up this webinar, are there any words of wisdom that you can share with high school students who might be thinking about biomedical engineering?
Yeah, I think that students who are interested in engineering, but really thinking about strong chemistry and biology backgrounds, biomedical engineering is usually a great fit for those students. So there are students who really like the engineering side of things, but maybe they're not as interested in the civil engineering or large-scale structural design, or maybe they're not interested in more of the electrical side of things. There's a whole branch of engineering within biomedical engineering that you can really focus on the chemistry and the biology. Again, it's also a great pathway for students who think that medical school might be something that they want to do, right? So it really does a good job of creating students who can think on their feet, who can do critical thinking and problem solving, and they usually become really good physicians. So it's a great pathway into medical school for those students as well.
All right. Well, thank you so much, Dr. Sell, and thank you to Elena, Gabby, Abby, and Eileen. This is a very cool firsthand look at what's going on in the tissue engineering lab today. For any of our viewers, if you would like to learn more about the engineering programs at SLU, please go ahead and visit slu.edu/parks. And as always, you can reach out to us at parksevents@slu.edu if you would like to connect further. And finally, please plan to join us next week for another webisode of our webinar series on Thursday, October 22nd at 1 p.m. And we will be visiting the engineering physics program. So thanks again for joining us and have a great rest of your day.